Hello everyone, welcome to this one Unit 3 quiz, this review. So problem 1 is asking us to draw reaction mechanisms for Fischer esterification and the reaction between acyl chloride and alcohol. Let's get started from Fischer esterification with isotope labeling. Here we are using oxygen 18. Oxygen, the major component of oxygen is oxygen 16. That's majority of isotope in highest natural abundance, but we have also small percentage of oxygen 18 available. Oxygen 18 is isotope. What is the meaning of isotope? Same number of protons, same number of electrons, but different number of neutrons. So its mass is different. Its mass is now heavier than oxygen 16. So its chemical properties are all the same. Number of valence electrons, their reactivity all the same. The only difference is this one has heavier mass, so we can detect this one with isotope labeling. So we are using isotope labeling in confirming or figuring out mechanism in organic chemistry, also trying to keep track of this isotope and figuring out metabolic pathway in biochemistry. Here, let's get started. We have excess amount of alcohol. Usually that's the case to make the equilibrium to the formation of the product, and we have sulfuric acid. It must be acid catalyzed or base catalyzed reaction because carboxylic acid is not reactive. So first, let's figure it out. We have hydrochloric acid, sulfuric acid. Sulfuric acid will be reacting with this alcohol. Alcohol is a weak base, and it will be moving toward the formation of the product. So it will be protonating the alcohol. It will be forming. So this one is isotope. Let me show the isotope right there, and it will be protonated. So this one is our acid available in the solution, and this one is our base. So this oxygen has two lone pairs. So this is our base. Okay, let's use back and forth using this one, acid-base reaction. I saw when I was grading this one, I saw many students make a mistake that like without activating the carboxylic acid, they try to do nucleophilic attack. That cannot work. Remember, our alcohol is a weak nucleophile. So let me write here again. So this is a weak nucleophile alcohol, and carboxylic acid is also weak electrophile. So then weak nucleophile, weak electrophile, they will now react with each other. So we need to first activate. The first step is activating this carboxylic acid by protonating it. Remember, so the first step must be protonation. So we have here acid available, and this one is strongly acidic condition. So then this one has two lone pairs, and let's activate it. Okay, and then remember all the steps are equilibrium, draw equilibrium arrow, not only the forward but also the backward, and let's draw this activated positive charge. Please draw the formal charges. I saw students forget or not knowing how to assign the formal charges. Here initially oxygen has two lone pairs. This one of the lone pairs has been used up in forming new oxygen hydrogen bond. So then oxygen carries positive charge now. So this is reactive because we have resonance structure right there. So this one has OH and carbocation, and this carbocation is a major chemical species. Major representative of the the resonance structure. Before it was a minor. Okay, this is the minor representation of the resonance structure. Okay, so now we have an alcohol. alcohol is a weak nucleophile, but now this activated carboxylic acid is really requiring the carbon has now like higher carbocation characteristic. So then use this one as a nucleophile. Okay, so then let's use this one. Let's grab the proton. Let's attack the carbon push up the pi bond to this oxygen. So we'll have equilibrium process again, and we have a new, let me erase it. We have a new carbon oxygen bond. So OH right there, and OH, and this one is now oxygen isotope, and hydrogen right there, and this one is now ethyl group. And this oxygen carries now positive charge because it has offered one of its lone pairs to the carbonyl carbon. Here, next, this acid-base reaction. So let me use this one. Acid-base reaction is very fast. So let's use our alcohol as deprotonating it. So we'll have this condition now, OH and oxygen, isotope oxygen, and fully available right there. So our goal is cleave this carbon oxygen bond, make them living. So in order to do that, we need to protonate. Currently, this one is a poor living group, and in acidic condition, we do not make them living. In basic condition, we can make it living, but in acidic condition, okay, we cannot leave them as it is. So we need to protonate first. So this one, we have acid available, and so acid is involved in catalytic quantity. Catalytic as a catalyst. So it will be protonated, becoming a good living group. So it will be becoming a good living group. OH right there. Here, OH2 now, positive charge, and OH lone pairs. And then again, this one is 2 lone pairs right there. Okay, now let's choose one of the lone pairs of oxygen, put it down, and kick out the good living group. So remember, this is good living group. Okay, so next one is forming all the way. Always draw two-way arrow, forward reverse arrow, because this one is equilibrium, all the equilibrium stage. So this one is now oxygen and positive charge, and then here this one, like, and finally deprotonation. Deprotonation. So this one is taking proton, it is moving to this oxygen, finally forming the product. Product is now ester. Okay, so this one becoming oxygen, and here. So when you draw it, please clearly show the presence of where is this, okay, the isotope. And the important step in the overall reaction is, first step is very important. So protonation is important. Let me show it. The first protonation is very important one. And then nucleophilic. So this one, let me write it clearly here. Nucleophilic attack. Nucleophilic attack is very important one. And also here, let me see. Loss of water. Here water is living, so loss of water is also important step. So loss of water, nucleophilic attack, and the first step, protonation and activation. This one is activating. activating the carboxylic acid by protonation. The first activating nucleophilic attack and then loss of water. These three are really core reactions in multiple step mechanism. Okay, now let's move up to B, nucleophilic acyl substitution reactions. Here, first recognize it. Alcohol is not acidic, not basic like water. Water itself is neutral. Alcohol itself is neutral. We have triethylamine, which is weak base. So this one is slightly basic condition. Okay, remember this is not acidic condition. So I saw some people try to protonate this oxygen, but there is no source of proton. Neutral condition was slightly basic condition, and plus this acid chloride is very reactive. So we don't need to protonate. Without protonation, the reaction will occur. That's the difference between this acid chloride versus ester or amide. Okay, so it will be, first one is simple nucleophilic attack as it is. So let's grab one of the lone pairs. Let's offer to the carbonyl carbon, push up pi bond to this oxygen. So it will be forming a nucleophilic attack, and it will be forming oxide ion. It will be forming tetrahedral intermediate and then oxygen. This is positive charge, and here propyl, normal propyl group. Okay, and this is chlorine. Remember, chlorine is a good leaving group. So this one is a good leaving group. So then carbonyl will be regenerated. So the lone pair coming down, and carbonyl group will be regenerated, and then chlorine will be leaving. It will be forming, and here propyl group right there, and let me use triethylamine as a base and take this one and forming ester, and here triethylamine is now positive charge. So chloride has left here, and this chloride left. So chloride will be forming this together. This salt will be formed. Okay, this one is a process, and then the final step will be irreversible, because ammonium ion is not a nucleophile at all. Chloride also trapped with this forming the salt, and ester will be remaining. This one is stable. Okay. Now let's move up to number 2, reaction of cyclopentane carboxylic acid with various reagents. Remember, this carboxylic acid reaction is very important. First, thionyl chloride, and it will be forming and acid chloride. Very important, thionyl chloride, and they will be generating sulfur dioxide gas. This will be bubbling out of solution. It will be forming HCl, and let's see. So because of this gas will be bubbling out of solution, the reaction becomes irreversible, and so it can be activating. The carboxylic acid is stable. Carboxylic acid and ester, their reactivity is about the same. They are stable, but acid chloride is very reactive, unstable. And how can it go against this stability? Because the sulfur dioxide gas is bubbling out of the solution. That's the motivation and driving force of this chemical reaction. And then from acid chloride, we can do many chemical reactions. So definitely we need to understand the reaction mechanisms and this result of chemical reaction. And then also see this hydrogen of carboxylic acid in acidic pK value around 4. For example, acetic acid pK value 4.8 and benzoic acid 4.5, something that range, 4 and a little bit higher than 4, a little bit less than 4, depending upon its structures. So remember, the carboxylic acid pK value is around 4. Among organic acid, this is most acidic. Second is Fischer esterification. When you have ester in acidic condition, this is Fischer esterification. Fischer esterification is very important. Please know how to draw the mechanism, how to figure out the structure. So then the product will be ester. Ester, and here we have oxygen right there. We have isopropyl group right there. And plus it will be forming water. So water is a byproduct. So by specific distillation method, we need to take out water because this is equilibrium process. And carboxylic acid, ester, they have a similar reactivity, similar stability, then this is equilibrium. And in order to make the reaction moving toward the formation of the product, we need to take out the water. And then by Le Chatelier's principle, the reaction will be moving toward formation of the product. And in the C, most of students did it wrong for C. And here we have amine. Amine is mild base. And carboxylic acid and acid. Then acid-base reaction will occur. So it will be forming protonated ammonium ion. And this one is pK value around 10. This is more stable than pK for carboxylic acid. Then it will be the acid-base reaction will occur fast, and it will be moving toward formation of the product. So this one, our carboxylic acid will be forming carboxylate ion, resonance stabilized. So the acid-base reaction occur and then stop there. Anything cannot happen. Ammonium ion is not nucleophile at all because it doesn't have now lone pair. Carboxylate ion is stabilized by resonance, so it is not reactive either. So then it will stop there. You can write this one as a product or simply write no reaction because nucleophilic reaction cannot happen. Okay, it'll be simply acid-base reaction. Okay, and D, it is excess amount of lithium aluminum hydride, and by acidic workup it'll be reducing carboxylic acid all the way to primary alcohol. So it'll be primary alcohol. I saw students mostly be correct like A, B, D, but C, majority of the students got it wrong. They were writing the what is it? I mean amide as a product. It is incorrect. If our reagent is not non-acidic like ester, or if it is an acyl chloride, the reaction will be occurring with amine, this primary amine to form amide. But here in this case, this is carboxylic acid. The most important characteristic of carboxylic acid is acidic, pK value 4. Okay, please remember this is acidic. That's the distinctly different from other carbonyl compound. Now let's reaction. Think about reaction of this lactone, cyclic ester. Okay, acid catalyzed or base catalyzed hydrolysis is very important, and the reaction of those other reagents is very important. First, let's think about excess amount of lithium aluminum hydride and acidic workup. Then it will be cleaving the bond right there. This one is okay, and it will be forming a primary alcohol. So here it will be becoming OH 1, 2, 3, and here it will become alcohol right there. Okay, and then B, NaOH. So this one is, second one is base catalyzed hydrolysis. Base catalyzed hydrolysis. So hydrolysis is very important. So make sure you understand how to draw the mechanism, how to figure out the product, hydrolysis. Hydrolysis. So then the carbonyl carbon and oxygen bond will be dissociated. It will be forming a carboxylic acid and the product. So then it will be forming carboxylic acid. So this one is newly formed chemical bonding, this one, and forming like this way. Erase it. So it's coming down, and here alcohol right there. And when you use this secondary amine with the heat, then amide will be forming. So it will be forming amide right there, nitrogen with ethyl group. Amide will be forming and coming down here, and it will be forming an alcohol. So one side is amide, the other side alcohol. And when you use excess amount of methyl magnesium iodide, this is Grignard reagent, excess amount, then twice this one, CH3, will be attacking it twice. And reforming the product, we'll have now alcohol, tertiary alcohol, and here methyl twice added, and then here alcohol right there. So then one side is primary alcohol, the other side is tertiary alcohol. And finally, when you use this diisobutyl H, diisobutyl alumino hydride, negative temperature is very important. You need to have negative 60 degrees C. In toluene also, solvent will be toluene, and acid work up, then it will be forming an aldehyde. It will be making it. It will be providing hydride, one hydride, only one equivalent hydride, and it will be turning this one into aldehyde, and it will be cleaving the bond. For the other side is not alcohol. So one side is aldehyde, the other side is alcohol. All right. Here in this case, 2 hydrogens added twice. Okay, primary alcohol. All right. Now let's write the reaction mechanism of this basic catalyzed hydrolysis. First, the hydroxide is strong nucleophile. Let's take the lone pair and attack the carbonyl carbon and push up the pi bond to this oxygen. So it is now here oxide ion right there, oxide and OH. Okay. And we have a leaving group right there. This oxygen is a lone pair. When you have oxygen, the substituent has lone pair, it can be leaving. So then carbon will regenerated, and the carbon oxygen bond is dissociating, and it is going to ring cleavage. So here and here, this is also equilibrium process. We have now oxygen, carboxylic acid one side. Let me erase it, this one right there, and here oxide ion. This becomes oxide. And remember, this kind of ring structure, now one side becoming oxide. Let me write it here. This one is strong base. Oxide is strong base, and the other side here the other side is carboxylic acid. Remember carboxylic acid now among all the organic acid, this is the most acidic. Except inorganic acid like sulfuric acid or hydrochloric acid. This is most acidic. Remember, this is most acidic. Then intramolecular reaction, acid-base reaction will occur. So oxide is strong base. So then acid-base reaction will occur. It will be forming carboxylate ion. And this one is practically irreversible. So far it is reversible. Now this is practically irreversible. Practically irreversible. Important. I saw many students, some of the students are missing this step. Okay. And what is the driving force of this reaction? Because of this step is irreversible, this is going to completion. So this side becoming carboxylate ion. And this becomes alcohol. So alcohol is a weak nucleophile. Carboxylate ion is very stable, resonance stabilized. Then reaction, it is remaining like that way. And then next one is protonation. So now we have this acid, hydronium ion is now added to the solution. Then this will be protonated, forming a final product. One side is becoming carboxylic acid, and the other side becoming a primary alcohol. Okay. So I want to really emphasize this step, internal acid-base reaction. Why this one is almost irreversible? Because of pKa values. This pKa of alcohol, pKa value of alcohol is 16. pKa value of this carboxylic acid is 4. So remember, in acid-base reaction, it is moving toward more stable. Okay, more stable acid, meaning pKa value larger value will be formed. pKa value 16 and 4, they are 12 difference. Remember, pKa is not negative log of Ka because it's logarithmic definition. Then pKa 12 meaning 10 to the 12th power difference in their concentration. 10 to the 12th power. That's why it is, practically speaking, irreversible. This is the driving force of the chemical reaction. Okay, now B, let's draw a twice of addition, two equivalents. Remember, this one, let me emphasize this one again. This one and two equivalents of Grignard reagent. Grignard reagents and lithium aluminum hydride, it will be added twice with ester and amide, or acid chloride or anhydride, any of these carboxylic acid derivatives, it will be reacting with twice. Okay, first let's write methyl magnesium iodide. So then methyl group has strong partial negative charge, magnesium partial charge. So we can treat this one as full carbon ion, full negative charge, and Mg I this way. And I saw some students draw like this way. Okay, it is incorrect because this means this is CH3 and CH2. Let me write here. This one is CH2 and CH3 negative charge. This is the meaning of this one. Okay, so simply draw CH3. Okay, then CH3, this carbon ion will attack, nucleophilic attack of this ester because this is so strong. Remember, carbon ion is the strongest nucleophile. Then it will be one side reaction and it will form a tetrahedral intermediate oxide ion right there, Then methyl group is neutral. Initially it is negative charge, now it becomes neutral. Next one, we have this oxygen has lone pair. When substituent has lone pair, the carbonyl is regenerated, and then this ring is dissociated. This one, okay, this is equilibrium process. Here, carbonyl is regenerated, and methyl right there, oxide ion, negative charge. Okay, and here we have excess amount of Grignard reagent, then this Grignard reagent will be even more reactive in reaction, so it will be forming the product. So then this one is oxide and 2 of methyl, and then forming oxide, and then protonation will be forming the product. So it will be OH, so tertiary alcohol, and the other side will be primary alcohol. This will be the product. So we are to see the review of this Unit 3 quiz. Please everyone take time to go over each of the reactions and then reaction mechanisms yourself. I recommend you, if you're not sure about the reactions or if your score is not enough for you, please go over this one 3 times. Okay, make blank page before you repeat the process, so you can have really confidence of drawing the mechanism and figuring out the product. Okay, everyone, thank you for being with me, and I'll see you next time.